Here's solutions to selected review problems for trig pre-cal. Let me start with 45. The task here is just to see the pattern and to write it with sigma notation. And so we need to find a general formula that's going to give these terms. So when k equals 1, now we get to choose the letter. I'm just going to choose k. They often use I, you can use whatever. Use it from the middle of the alphabet to suggest that it's an integer though. When k equals 1, we want a sub k to be 3. When k equals 2, we want a sub 1 in other words. We want a sub 2 to be equal to 6. K equals 3, we want a sub 3 to equal 9. So we need to find the pattern. I just wanted to write this out very explicitly to be able to check if we're getting the right pattern. Well, this pattern is not some random sequence of numbers. It's going up by 3 each time. So key thing here is that there's a common difference. D equals 3. Aha. Okay, so that's an arithmetic sequence. So this is not something where we have to guess around a lot for the sequence. We know how to get the formula for that, and that is a sub n or k or whatever. Let's do k because I usually do k inside a summation. A sub k is going to be a, or a sub 1, whatever you want to call it, times k minus 1 times d. You start at your first thing in the sequence, and then you do a certain number of steps of d. You don't do k steps. You do how many more have you gone up from 1, that's k minus 1. And we know a sub 1, that's 3, and we know our d is 3, so I'll put that in front. Or in other words, a sub k, is 3k. Now, we could have, even if we had never heard of an arithmetic sequence before, we probably could have figured out that formula, that if all I'm doing is I'm tripling the label k to get the actual number in the sequence, a sub k is 3k. But it is an example of an arithmetic sequence. Now, what did we want? We wanted to express this in summation notation. And so this is the sum from k equals 1, and that was our choice to start counting equals 1. That's why this formula was correct. Up to, and then we still need to know that, up to some n of this formula 3k. Okay, so let's go back up for 1 second, and we know that a sub n, so here's why I use k, and they often use k for, not always, but here's a good reason to use k for the internal sum. I want a name, at least temporarily, for how many terms there are total in the sequence. K is something that's a dummy variable. It's a temporary variable that steps from 1, 2, 3, 4 and labels the particular terms in the sum. But n for me right now is how many terms are there? Well, we know that the general formula is 3n, and we know that needs to be 99, and that solves to be n equals 33. So this is the 33rd term in the sequence, and so that's going to be 33. Hopefully that might seem like belaboring a problem. It doesn't. You don't have to do it with this much detail, but that's a very systematic way to do it. If this weren't such a particularly simple arithmetic sequence, this whole process would have been much more necessary. But that's the summation that we get. And then what did I want to do? 47. 47, same kind of thing. We've got 1 times 2 cubed plus 2 times 2 to the 4th plus 3 times 2 to the 5th plus plus up to 100 times 2 to the 102. Okay, so when k equals 1, that means that a sub 1, the first term in the sequence, is 1 times 2 to the 3. So this 1 seems to match this 1 exactly. But the 3 is 2 more than that. Let's see if that pattern holds true as we go. The next term, which should be have the label k equals 2, is 2 times 2. That's always staying constant, that base, times 2 to the 4. Okay, it's still true that these two match, but this is 2 more than this guy. So in general, our general formula for a sub k is going to be k times 2 to the something that's 2 bigger, in other words, k plus 2. And so our summation, if we want to write this as the whole pattern, k equals 1. We made sure that we started with k equals 1, and that made this formula correct. If we had started with k equals 0, we could have had a slightly different formula. It's really up to us where to start, but k equals 1 is a pretty good default. And I'm not sure how far to go, just we'll figure that in 1 second. That's usually what you end up figuring out last. And then k, just the general formula, k times 2 to the k plus 2. And then, let's see. What's this last one? That's where this one is 100. Well, that was matching the end, so this is pretty easy because this actually matches the term you're at, and so that's just going to be 1 to 100. Okay, and so that's going to be what this is equal to. Let me just, pasted it in the wrong place. There we go. There's our final answer. Okay, and moving on to 59. 59, that's a financial one. Okay, so we want periodic investment. Okay, so we know that if I invest, let's say D amount each, now this is each quarter, that's 4 times a year, so 1/4 of a year. Each D amount each quarter for 1 year. Oh, okay. So that's 4 quarters. Okay, and 12% at 12% annual rate. Oops. Well, that's a 3% quarterly interest. Remember, we always take that annual rate and we divide it by however many times the compounding happens. Okay. Well, what's that going to be? We know that that's going to be D. That's one of the investments. That's the one that hasn't earned any interest. And then plus 1.03. That's the investment that has earned interest once. Plus D 1.03 squared plus D 1.03 cubed. Now, it kind of depends, and you know what? I should check the answer in the back, but it kind of depends on exactly how we account this. If it's if we've only earned interest on 3 of these guys and not the last one, then it's this formula. And that's what I've been usually emphasizing because it's kind of the cleanest formula mathematically. We could imagine something where we invested it and they gave us interest afterwards, in which case we've gotten this interest on this 4 times, this 3, this 2, and this 1. So this would have a 1.03. They're going to be different by a factor of 1.03. But let's try this one. This guy, it's kind of a pain to collect and solve this, and it would be a huge pain if this is like 75 or something like that, or 2,000. And so it's nice to know that there's a shortcut formula for that. That's D, which is what we usually call A. That's our first term, times 1 minus 1.03 to the next power over 1 minus 1.03. Okay, that's a little bit tidier. Oops. Okay. And so that's D. And then what is it? This 1 minus 1.03, that's minus 0.03 times 1 minus 1.03 to the 4th. And that minus sign's kind of annoying. And let's use it to switch around this guy. The general formula here is the deposit divided by the rate times 1 plus the rate to the n minus 1. Now here, n is how many periods you've done, and r has to be the rate per period. And so it's not a 12%. That's why this 3% quarterly had to come in. So that can be a little subtle. Okay, so I'm just pointing out there is sort of a master formula for this, which you may or may not want to memorize or write down in your notes. Okay, so now what's the idea here? We want to have 10,000. 10,000 is supposed to be equal to all this. And so D is going to be equal to 0.03 times 10,000, which is going to be 300, all divided by this guy. Okay, and that I might as well let the calculator do. And so it looks like 23, 90, 30, about. It might be off by a cent because it usually only goes to 5 places by default. Okay, so that's how much I have to put in. So it's not a huge surprise. I'm not getting a lot of interest, and it's not a ridiculous interest rate, and I'm not leaving it in there for very long. It's only a year. So I pretty much have to put in almost $10,000 to get $10,000 out. But this isn't $2,500 is the point. If this was $2,500, well then yeah, I put in $10,000. Here I put in a little bit less, and I get $10,000 out from the interest. Okay, and one more before I quit this video. 63. Oh yeah, just a sum of an infinite geometric series. 1 plus 3 to the 1/2 plus 1 over 3 plus 1 over 3 to the 3/2 plus dot dot dot. Okay. Alrighty. You know, I'm thinking somehow, I don't know if I put in any I think I forgot to put in some repeating decimal problems in here. I should do that, make sure there's some more in there. Okay, so that's going to be, it's an infinite geometric series, so it's an easier formula. It's a over 1 minus r. We just have to figure out what a and r are. Well, a is 1. That's what we start with. It's always the first term. That's easy. And then r, what's the common ratio? At every stage I'm multiplying by 1 over 3 to the 1/2. Because 1 over 3 to the 1/2, that's 1 over square root of 3. If I multiply that by itself, I get 1/3. If I multiply it by that again, I get 3 to the 3/2, etc. This really is an infinite geometric series as advertised. And the ratio is 1 over root 3. And so I just have to simplify that. It's a compound fraction, so let's just multiply by root 3 top and bottom. Okay, so that's going to turn this 1 into a root 3. It's going to cancel this out and turn it into a root 3. That's cleaner if I don't have those. Okay, and now, oh, you know, I do have to rationalize that. So I just let's write it again. Could have just copied it, I guess. And then I do the conjugate, top and bottom. And so I get 3 plus root 3 over root 3 times root 3 is 3, minus 1 is 1, so we get 2. And that's a good answer. Okay, good place to stop.